In the summer of 2025, astronomers detected something moving through our solar system at 153,000 miles per hour. They called it a comet. But what if they were wrong? What if 3I Atlas isn't ice and dust, but something far denser, far heavier, something capable of pulling planets from their orbits? While you were sleeping, Japan issued a historic megaquake warning. Internet servers across the globe experienced synchronized failures that engineers can't explain. The sun erupted with flares nobody predicted, and according to some models, Mercury has already begun its death spiral. Stay with us until the end, because what we're about to reveal suggests Earth has 50 years before we're expelled into the cosmic dark. The clock started ticking months ago. If you're as captivated by these cosmic puzzles as I am, go ahead and like this video and subscribe to stay connected as we continue tracking this story. Leave a comment telling us where you're watching from, what hour it is in your corner of the world, and whether you think the full picture is being shared with us about what 3I Atlas really means for our future. Part 1. The gravitational wrecking ball arrives. In the summer of 2025, astronomers scanning the sky picked up something unusual. The object moved fast, far too fast to belong to our solar system. Its trajectory traced a hyperbolic arc, the telltale signature of an interstellar visitor. They catalogued it as 3I Atlas, the third known interstellar object ever detected passing through our cosmic neighbourhood. The scientific community issued the standard reassurances. This was a comet, they said, just ice and rock from another star system, swinging through on its way back to the galaxy. Nothing to worry about. But in the months that followed, something shifted. Whispers began circulating in astronomy forums and research groups. The data coming back from 3I Atlas didn't quite fit the comfortable narrative of a harmless icy wanderer. What if we've been looking at this wrong? What if 3I Atlas isn't a comet at all, but something far more dangerous? The official measurements paint an intriguing picture. When discovered, 3I Atlas was screaming through space at roughly 137,000 miles per hour. As it approached the Sun, it accelerated to about 153,000 miles per hour near perihelion. The nucleus, the solid heart of this visitor, measures somewhere between 440 meters and 5.6 kilometers across. Those numbers alone tell us this object possesses serious mass. Its orbit is unambiguous. 3I Atlas will not circle back. It's on a one-way trip through our solar system and then out into the void forever. The mainstream view remains unchanged. NASA and other space agencies classify 3I Atlas as an interstellar comet. They point to the coma, the fuzzy cloud of gas and dust surrounding the nucleus. They note the tail streaming behind it as solar radiation pushes material away. They measure the outgassing, the jets of vapour erupting from the surface as sunlight warms the ice. Every indicator suggests a typical comet, albeit one from another star. The closest approach to Earth came out to roughly 1.8 astronomical units. That's far enough that even a significant gravitational field would barely register here. No danger, they insist. Case closed, except the anomalies keep piling up. Recent polarimetric studies revealed something unprecedented. 3I Atlas exhibits what scientists call a deep and narrow negative polarization branch. This pattern has never been observed in any asteroid or comet before. The way light scatters off its surface doesn't match anything in our catalogues. Then came the chemical analysis. Spectroscopy and photometry studies suggest this object might contain substantial amounts of metal. One paper describes it as a primitive metal-rich interstellar body, possibly carbonaceous in composition. That's not the profile of a typical icy comet. That's something different. Something processed by stellar events we barely understand. These oddities crack open a door to alternative possibilities. Perhaps 3I Atlas isn't a low-mass chunk of ice and dust. Perhaps it's dense, compact, structured differently than anything we've seen before. Some researchers have begun entertaining more exotic scenarios. What if this visitor carries unusual mass distribution? What if its gravitational influence extends beyond what we'd expect from a comet of its apparent size? Imagine for a moment that 3I Atlas is indeed a dense, heavy body. Not exotic matter from science fiction, but simply far more massive than its brightness and coma suggest. Gravitational forces drop off with distance, yes, but they never disappear completely. A sufficiently massive object swinging through the inner solar system could, in theory, create subtle perturbations. It could tug on planetary orbits, It could distort local space-time. It could generate tidal stresses on planets it passes. The stakes become clear when you think about what gravitational disruption means for Earth. Our planet exists in a delicate gravitational balance. The Moon stabilizes our axial tilt. Jupiter's gravity shields us from some asteroid impacts, but also perturbs comet orbits. The inner planets maintain orbital resonances that have persisted for billions of years. Any significant external force threatens that balance. If 3I Atlas were indeed a gravitational wrecking ball, its passage might throw off more than just our calculations. It might throw off our entire orbital architecture. But this is only the beginning of the story. In the parts ahead, we'll examine strange events that occurred in the months around 3I Atlas's perihelion. A historic megaquake alert in Japan that had seismologists scrambling. Internet infrastructure failures that some network engineers claim shouldn't be possible. Solar flares of unexpected intensity erupting from the sun. Orbital simulations that predict catastrophic outcomes over the coming decades. Each piece of evidence raises the same unsettling question. What if 3I Atlas already triggered something we haven't fully recognized? What if the wrecking ball has already swung through and we're only now starting to feel the impact? The object is receding now, moving back toward interstellar space at tremendous speed. But gravitational effects don't always manifest immediately. Orbital perturbations can take years or decades to compound into visible changes. Tidal stresses might weaken fault lines that won't rupture until much later. If 3I Atlas did leave a mark on our solar system, we might be living through the opening act of a transformation we don't yet understand. The scientists continue their observations. Telescopes track the fading dot as it retreats into the dark. They refine their models, analyse more spectra, debate the composition in peer-reviewed journals. Most remain confident that 3I Atlas poses no threat. But a small number of researchers, working quietly at the edges of the mainstream, wonder if we're missing something crucial. They wonder if the standard Comet models fail to capture the full reality of this visitor. They wonder if we should be preparing for consequences we haven't imagined. Part 2, Japan's megaquake advisory, the first symptom. The Japan Meteorological Agency doesn't issue megaquake advisories lightly. When they released their warning, the nation went on high alert. Emergency supplies flew off shelves. Coastal communities reviewed evacuation routes. The media filled with images of fault lines, subduction zones, and computer models showing potential tsunami inundation. Japan has lived with seismic danger for millennia, but this warning carried unusual weight. Scientists pointed to increased activity along the Nankai Trough, a subduction zone where the Philippine sea plate dives beneath the Eurasian plate. Historically, this region has produced magnitude 9 earthquakes. The advisory suggested another might be imminent. Mainstream seismology explains these events through plate tectonics. The Earth's crust consists of massive plates floating on the semi-molten mantle. Where plates collide, one typically slides beneath the other. Friction prevents smooth motion, so stress builds over decades or centuries until the rock finally fails. The sudden release produces earthquakes. The Nankai Trough accumulates stress constantly as the Philippine sea plate grinds beneath Japan. Eventually, that stress will release catastrophically. The question isn't whether another megaquake will strike, but when. Yet some independent researchers have begun asking a different question. What if external forces can trigger earthquakes by adding just enough stress to push an already loaded fault past its breaking point? What if 3I Atlas provided that final push? The hypothesis sounds radical at first. Earthquakes come from below, from the grinding of tectonic plates kilometers underground. How could something in space influence that? The answer lies in tidal forces. The Moon raises ocean tides by pulling on Earth's water, but it also raises tides in the solid Earth itself. The ground beneath your feet rises and falls by centimeters as the Moon orbits. These Earth tides are small, but they're real and measurable. They can influence the timing of earthquakes by adding or subtracting stress on fault zones at critical moments. Now scale that up. Imagine an object far more massive than it appears, passing within a few astronomical units of Earth. Its gravitational field would create tidal forces, stretching Earth slightly along the direction toward the object, and compressing it perpendicular to that direction. The magnitude depends on the mass and distance. For a typical comet, the effect would be negligible, far weaker than lunar tides. But if 3I Atlas was substantially denser or more massive than standard models suggest, those tidal forces could multiply. The timing alignment raises eyebrows. 3i Atlas passed through the ecliptic plane during the same general window when seismic activity increased in Japan. Some analysts on specialized forums claim this can't be coincidence. They argue the gravitational interaction stressed the Nankai Trough just enough to elevate earthquake probability. It's the cosmic equivalent of the straw breaking the camel's back. The fault was already primed, already near failure. 3i Atlas just nudged it closer to the edge. But here's where the theory runs into trouble. We have GPS networks blanketing Japan and much of the globe. These networks detect ground motion with millimeter precision. If tidal forces from 3i Atlas were strong enough to stress fault zones meaningfully, GPS would show it. The ground would deform measurably. We'd see the strain accumulate in real time. Yet no published GPS data shows anomalous deformation correlating with 3i Atlas's trajectory. The crust behaved exactly as expected based on plate tectonics alone. Consider the physics more carefully. Tidal force drops off with the cube of distance, double the distance, and tidal force decreases by a factor of 8. 3i Atlas passed Earth at 1.8 astronomical units, more than 250 times farther than the Moon. Even if it were as massive as a small asteroid, hundreds of times heavier than a typical comet, the tidal forces at that distance would still be orders of magnitude weaker than lunar tides. To generate stresses comparable to what the Moon produces, 3i Atlas would need to be astronomically massive or pass astronomically close. Neither matches observation. Let's be generous and run a thought experiment. Assume 3i Atlas somehow conceals enormous mass, perhaps as a super-dense core wrapped in a deceptive icy exterior. Assume it passed at the observed distance with this hidden mass. The tidal gradient it produces depends on both total mass and the variation in gravitational pull across Earth's diameter. You can calculate this. Even with wildly optimistic assumptions about hidden mass, the resulting tidal stress comes out minuscule compared to the tectonic stresses already present in subduction zones. Earthquake triggering requires adding stress of at least several kilopascals at the fault depth. 3i Atlas, under even extreme assumptions, wouldn't deliver a fraction of that. The alternative explanations remain far more convincing. Subduction zones accumulate stress inexorably as plates converge. The Nankai Trough has been loading since the last major rupture. Smaller earthquakes, slow slip events, and fluid pressure changes in the fault zone all contribute to an evolving stress state. When seismologists issue megaquake warnings, they're responding to this internal evolution of the fault system, not cosmic influences. The timing alignment with 3i Atlas is just that, an alignment. Coincidences happen frequently when you track enough variables. Yet the theory persists in certain corners of the internet. Part of the appeal lies in the human tendency to seek dramatic causes for dramatic events. A megaquake triggered by internal plate tectonics sounds mundane. A megaquake triggered by a mysterious interstellar visitor sounds profound, almost poetic. We're drawn to stories where cosmic and terrestrial events connect. We want the universe to be more interconnected than it actually is. That cognitive bias makes external trigger theories attractive regardless of their physical plausibility. There's also the unpredictability factor. Earthquakes remain notoriously difficult to forecast precisely. We know where they'll happen, we know roughly how large they can be, but we can't pin down when. That uncertainty creates space for alternative explanations. If the standard model can't predict earthquakes perfectly, maybe there's something else at play. 3i Atlas offers a convenient scapegoat, a way to fill the gaps in our understanding with something tangible. So where does this leave us? Mainstream geophysics sees no connection between 3i Atlas and seismic activity. The gravitational effects are too weak, the distance too great, the observational evidence absent. But the speculation continues because it satisfies a deeper psychological need. It transforms random tectonic violence into part of a larger cosmic narrative. Whether that narrative reflects reality is another question entirely. What we know for certain is that Japan sits above an active subduction zone that will eventually rupture again. The megaquake is coming, with or without help from interstellar visitors. Perhaps the more unsettling truth is that Earth's geology needs no cosmic assistance to generate catastrophe. The danger was always here, grinding away beneath our feet, waiting for the right moment to release. Part 3. The Internet glitches that shouldn't exist. Over a span of just a few days, something strange rippled through the Internet's infrastructure. Major backbone providers reported unusual outages. Networks that had run smoothly for years suddenly experienced synchronization failures. Financial systems stuttered. Cloud services went dark briefly in scattered regions. Customer support lines lit up with complaints about sluggish connections and failed transactions. The official explanations came quickly. Software updates had gone wrong. Misconfigurations in routing tables had propagated across networks. Hardware failures at key data centers had created cascading problems. Nothing to see here. Move along. But in the darker corners of technical forums, some engineers weren't buying it. These weren't just any engineers. They manage critical infrastructure, the time servers and routing nodes that keep the internet synchronized globally. They noticed something the public statements didn't address. The glitches occurred at specific times that roughly aligned with 3i Atlas passing certain positions relative to Earth. More troublingly, they claimed to see microdrifts in atomic clock synchronization. Network time protocol servers, which use atomic clocks to timestamp every packet flowing through the internet, briefly disagreed with each other by milliseconds. That shouldn't be possible. Atomic clocks are phenomenally stable, accurate to nanoseconds over months. When they drift apart suddenly, even by small amounts, it suggests either hardware failure or something affecting time itself. The theory they whispered about involved general relativity. Massive objects warped space-time. Near a black hole, time runs slower than in flat space. GPS satellites have to correct for relativistic effects because time runs slightly faster in their weaker gravitational field compared to Earth's surface. If 3i Atlas was sufficiently massive, its passage could theoretically create local variations in gravitational field strength. As it moved past Earth, space-time would compress and stretch subtly. Atomic clocks in different locations might find themselves in slightly different gravitational potentials, causing them to tick at fractionally different rates. Network synchronization protocols depend on all clocks agreeing. If they don't, encrypted connections fail because timestamps don't match. Packets arrive out of order. The whole delicate timing infrastructure of modern internet communication breaks down. But let's examine what this would actually require. Gravitational time dilation scales with the strength of the gravitational field. At Earth's surface, we live in a gravitational potential that causes time to run slower than it would in deep space by about 1 part in a billion. A GPS satellite higher in Earth's gravity well experiences time running faster by about 45 microseconds per day compared to ground-based clocks. To produce even millisecond-scale time differences between locations on Earth's surface, you'd need a gravitational gradient far stronger than Earth's own field. 3i Atlas passed at 1.8 astronomical units. At that distance, even an object with Earth's entire mass would produce gravitational effects on our surface that are utterly negligible compared to the planet beneath our feet. For 3i Atlas to create measurable time dilation, it would need to be not just massive, but incomprehensibly dense and massive. We're talking stellar mass objects, neutron stars, black holes. Nothing with those properties could masquerade as a comet. Its gravitational influence would tear apart satellites, perturb the moon's orbit, create obvious and dramatic effects throughout the solar system. We'd know immediately if something that massive passed through. The energy budget makes this theory even more implausible. Space-time curvature requires mass energy. The amount needed to warp space-time enough to desynchronize atomic clocks by milliseconds would be astronomical. You can't hide that much mass. It would shine in gravitational lensing observations. It would perturb every asteroid and comet in its vicinity. Deep space tracking networks would detect the anomalies. The fact that none of this occurred tells us the object doesn't carry nearly enough mass to affect network timing. So what really happened? The mundane explanations remain far more plausible. Software updates do go wrong. Modern networks are staggeringly complex with billions of lines of code and millions of interconnected components. Bugs slip through. Configuration errors propagate. Sometimes multiple unrelated failures hit at once, creating the appearance of coordination. Network time protocol synchronization can be disrupted by signal interference, packet loss, hardware glitches, or even solar activity affecting radio communications. None of these require exotic physics, yet the conspiracy version has legs. Some engineers claim the public statements don't match the internal discussions they witnessed. They suggest companies quietly corrected timestamp anomalies without admitting the cause. They point to unexplained reboots of critical infrastructure at odd hours. They whisper about Bitcoin mining operations that saw hash rate fluctuations that day, implying time synchronization issues affected even cryptocurrency networks. But whispers aren't evidence. Private discussions aren't peer-reviewed data. In the absence of verifiable logs showing anomalous clock behavior tied to 3i Atlas's position, these remain allegations. There's a broad phenomenon at play here. Complex systems fail in complex ways. When the internet glitches, we demand simple explanations. Sometimes the truth is that no single cause exists. Multiple small failures combine to produce visible disruption. Our minds resist that ambiguity. We prefer narratives with clear villains or causes. 3i Atlas serves that psychological need perfectly. It's mysterious, it's external, it's conveniently timed. Blaming the comet makes more emotional sense than accepting that our infrastructure occasionally fails for boring reasons. The appeal of the relativistic explanation also reflects a deeper fascination with time itself. Time dilation sounds exotic and mind-bending. The idea that gravity can literally slow or speed clocks captures imagination in ways that server misconfigurations never could. We want to believe we're living through something cosmically significant, not just another routine network outage. The truth is probably disappointing. The glitches were glitches, nothing more. But the fact that people reached for gravitational time dilation as an explanation reveals how ready we are to connect everyday problems to cosmic events. What if the real story isn't about what 3i Atlas did, but about what we want it to have done? Maybe the outages were genuine technical failures, and the timing with 3i Atlas was pure coincidence. Maybe some engineers saw patterns that weren't there, primed by all the other speculation about this interstellar visitor. Maybe we're so hungry for cosmic significance that we'll read it into anything, even milliseconds of clock drift that probably never happened the way the stories claim. The internet runs on incredibly precise timing, yes, but it also runs on fallible hardware, buggy software, and human error. Those remain far more likely culprits than space-time warping from a distant comet. Still, the story refuses to die completely. Because what if, just what if, there's a grain of truth buried in the noise? What if some of those engineers really did see something they couldn't explain? Part 4. Solar Overdrive. AR4294 as a reactor on the edge. The sun woke up angry. In the weeks surrounding 3i Atlas's perihelion, solar observatories recorded a series of powerful X-class flares erupting from a massive active region designated AR4294. These weren't gentle solar burps. These were violent releases of magnetic energy, hurling plasma and radiation into space at millions of miles per hour. Coronal mass ejections followed, vast bubbles of magnetized gas tearing away from the solar atmosphere. When directed toward Earth, these storms can disrupt satellites, damage power grids, and create aurora visible far from the poles. The sun had entered an active phase, climbing toward solar maximum in its 11-year cycle. But some observers noted the intensity seemed excessive even for this stage of the cycle. Solar physicists had predicted increased activity. Yes, but not quite this much. Not quite this violent. Standard solar physics explains active regions through internal dynamics. The sun is a roiling ball of plasma threaded with magnetic fields. These fields are generated by the churning motion of electrically conductive material in the convection zone beneath the surface. As plasma rises and falls, it drags magnetic field lines along, twisting and tangling them into complex structures. Where fields emerge through the surface, they suppress convection, creating cooler regions we observe as sunspots. The twisted magnetic topology stores enormous energy. When the fields reconnect suddenly, snapping into simpler configurations that stored energy releases explosively as a solar flare. This is normal solar behavior, driven entirely by processes inside the sun. But a fringe theory has emerged, connecting these flares to 3i Atlas. The argument goes like this. The sun sits at the centre of the heliosphere, a bubble of solar wind and magnetic field extending billions of miles into space. This heliospheric magnetic field isn't uniform. It has structure, with a current sheet that warps and ripples like a ballerina's skirt. When a massive object passes through the inner solar system, it could theoretically interact with this magnetic structure. Not through direct contact, but through gravitational perturbation of the plasma that carries the magnetic field. Imagine swirling cream into coffee. The patterns are smooth until you add a disturbance. Then everything gets chaotic. 3I Atlas, according to this theory, acted as that disturbance. The proposed mechanism involves the heliospheric current sheet. This thin region separates regions where the sun's magnetic field points outward from regions where it points inward. Plasma flows along this sheet, carrying electrical currents that help maintain the overall heliospheric magnetic structure. If a massive body passed through at the right angle, its gravity could compress or stretch the current sheet locally. That distortion might propagate back toward the sun, carried by alpha waves, disturbances in magnetized plasma that travel at specific speeds determined by magnetic field strength and plasma density. Once these waves reach the sun's surface, they could trigger instabilities in active regions that were already primed to flare. The external object doesn't create the flare directly, it just provides the final push, the straw that breaks the magnetic camel's back. Calculating whether this could actually happen requires looking at scales and energies. The heliospheric current sheet extends several astronomical units from the sun. 3I Atlas passed well within that structure, but the sheet is diffuse, barely distinguishable from the surrounding solar wind in terms of density. A comet-sized object ploughing through it would create a wake, true, but an incredibly small one relative to the sheet's overall size. The gravitational influence would be localized to within a few comet radii. Beyond that, the effect drops off rapidly. For any significant disturbance to propagate all the way back to the sun, 3I Atlas would need to carry far more mass than observations suggest. Let's look at the energy budget. A major solar flare releases energy equivalent to millions of hydrogen bombs, typically 10 to the 26th to 10 to the 27th joules. That energy comes from magnetic reconnection in the solar atmosphere, where tangled fields snap back into simpler configurations. The magnetic energy stored in an active region can be estimated from the field's strength and volume. For AR-4294 to produce X-class flares, it needed to store and release that much energy locally. 3I Atlas passing through the outer heliosphere kilometers from the sun carries nowhere near enough gravitational or kinetic energy to influence those magnetic processes in any meaningful way. There's also the historical comparison. Comets pass near the sun constantly. Kreutz sungrazer comets dive through the corona and evaporate entirely. These comets come far closer than 3I Atlas ever did, plunging through the sun's outer atmosphere where magnetic fields are strongest and plasma is densest. Yet no correlation exists between sungrazer passages and solar flare rates. If comets could trigger flares, we'd see it all the time with these suicide plungers. We don't. The sun flares when its internal dynamics dictate, regardless of what falls into it. Recent spectroscopic observations of 3I Atlas itself undercut the massive disturber theory further. Studies using space-based infrared telescopes show the Comet is dominated by carbon dioxide, with substantial carbon monoxide, water ice and dust. This is classic comet behaviour. The nucleus is outgassing as it heats up, releasing volatiles trapped since the object formed in some distant stellar system. These observations allow scientists to estimate mass loss rates. From those rates and the observed brightness, they can constrain the total mass. The results consistently point to a relatively modest object, maybe billions of tons at most. That's peanuts compared to what you'd need to perturb anything on solar system scales. So why does the connection between 3I Atlas and solar activity persist? Part of it is timing. Humans are pattern-seeking creatures. When two unusual things happen around the same time, we assume connection even when none exists. 3I Atlas passed through while the sun ramped up activity. The correlation is tempting. But solar cycle 25 was predicted to produce increased activity in 2025, regardless of any interstellar visitors. The flares from AR-4294 fit perfectly within expected behaviour for this phase of the cycle. There's also the appeal of cosmic conspiracy, the idea that the authorities know more than they're telling. If the sun really were being destabilised by an external object, space agencies would be tracking it obsessively. The lack of public alarm becomes evidence of cover-up rather than evidence that nothing unusual is happening. This kind of logic is difficult to counter because it interprets absence of evidence as evidence of conspiracy. Yet the simpler explanation remains that the sun is just being the sun, following its normal cycle of activity driven by internal magnetic processes we understand reasonably well. 3I Atlas is a spectator, not a participant. But if the wrecking ball theory is wrong about solar activity, could it still be right about something else? Could 3i Atlas be quietly reshaping orbits? Part 5, The Orbital Chaos, Trigger Simulation. Somewhere in the digital wilderness of online astronomy forums, a simulation appeared. The author claimed to have used professional-grade orbital dynamics software, the same tools NASA uses to plan missions and track near-Earth asteroids. But instead of using standard mass estimates for 3i Atlas, this modeler made a radical assumption. They treated the object as ultra-dense, packing perhaps 10 to 100 times more mass into its volume than any normal comet should. With that assumption loaded into the simulation, they ran the clock forward. What came out wasn't reassuring. Orbital mechanics operates on principles Newton laid down centuries ago, refined by Einstein's general relativity for extreme conditions. Planets orbit the Sun in ellipses, their paths determined by the gravitational pull of the Sun and the subtle tugs from other planets. This system has remained stable for billions of years. Stability doesn't mean the orbits never change. They do, slowly, as planets tug on each other. Jupiter's immense gravity shepherds the inner solar system, preventing asteroids from accumulating in certain orbital zones. The resonances between planets' orbital periods help maintain long-term stability. If something disrupts these resonances, the whole architecture can unravel over time. The simulation in question started with 3i Atlas swinging through the inner solar system on its hyperbolic trajectory. As it passed, the massive gravity in this speculative model tugged on Mercury, Venus, Earth, and Mars. The perturbations were small initially, shifting each planet's velocity by a few meters per second. In the short term, those changes meant nothing. But gravity is patient. Over thousands of orbits, tiny perturbations compound. Mercury's orbit, already the most eccentric and unstable of the inner planets, became more elliptical. Its perihelion precessed faster than usual. Within a few decades of simulation time, Mercury's orbit intersected more closely with Venus's path. The two planets began a gravitational dance, exchanging energy every time they approached each other closely. Eventually, in one of the simulation runs, Mercury's orbit destabilized completely. The tiny planet either plunged into the Sun or was flung outward into the asteroid belt. Mars suffered a different fate. The perturbation from 3i Atlas nudged it slightly outward. Over the course of 50 simulated years, that outward drift continued as resonances with Jupiter compounded the effect. Mars slowly spiraled away from the Sun, its orbit expanding by tens of millions of kilometers. With increased distance, solar radiation weakened. Surface temperatures that once allowed brief liquid water now dropped permanently below freezing. Any remaining water ice locked itself into permafrost. The planet's already thin atmosphere froze out onto the poles. Mars became a frozen tomb, receding into the outer solar system. Earth's changes were subtler but more catastrophic for life. The simulation showed a gradual shift in axial tilt. Earth's axis, currently tilted at 23.5 degrees, wobbled. Over decades, that tilt increased by several degrees. This doesn't sound like much, but the consequences are profound. Axial tilt determines the severity of seasons. A larger tilt means more extreme temperature differences between summer and winter. Polar regions receive more sunlight in summer, less in winter. Ice caps destabilize. Ocean currents, driven partly by temperature gradients, shift. Weather patterns that have persisted for thousands of years break down. Monsoons fail or strike in unexpected locations. Agricultural zones that once reliably produced food turn into deserts or floodplains. Civilization, built on the assumption of stable climate patterns, collapses under the strain. But the simulation didn't stop there. Earth's orbit itself began to elongate. Its eccentricity increased, meaning the difference between closest and farthest distance from the Sun grew. This created a new problem. An elongated orbit means less solar energy reaches Earth during part of the year. Winters grow harsher. Growing seasons shorten. Ice ages that should take tens of thousands of years to develop might arrive in centuries. The combined effect of axis tilt and orbital elongation created a feedback loop. More ice reflects more sunlight, cooling the planet further, creating more ice. Earth slid toward a frozen state not seen since the snowball Earth events of deep time. The simulation's most disturbing outcome involved long-term ejection. As Earth's orbit stretched and its interactions with Venus and Jupiter changed, The accumulated perturbations over a century approached a critical threshold. In some runs, Earth's orbit became so elliptical and energetically disturbed that Jupiter's gravity could no longer keep it bound tightly to the inner solar system. The planet drifted outward over the course of several centuries, becoming a rogue world in the outer solar system, then eventually escaping into interstellar space. This wasn't explosive. No sudden catastrophe. Just a slow, inexorable slide into the cold dark. Now let's step back and examine what this simulation actually represents. It's a thought experiment based on one enormous assumption, that 3I Atlas is far more massive than all observational evidence indicates. The spectroscopic data shows a coma composition consistent with a typical comet. The brightness and tail behaviour match models assuming a relatively small icy nucleus. Estimates put the mass somewhere between 10 to the 12th and 10 to the 15 kilograms. That's billions to trillions of tons, yes, but it's nothing compared to the mass of even a small moon. For comparison, Earth's moon weighs 7.3 times 10 to the 22 kilograms. 3I Atlas would need to be tens of thousands to millions of times more massive than observations allow to produce the orbital chaos shown in that simulation. The modeler tried to justify the extreme density by invoking exotic matter or neutronium, the ultra-dense material found in neutron star cores. Neutronium packs the mass of an entire star into a sphere kilometres across. A neutronium fragment the size of 3I Atlas would indeed carry terrifying mass. But there's no plausible mechanism for such material to exist as a wandering object. Neutronium only remains stable under the crushing gravity of a neutron star. Remove that pressure and it explodes instantly. A neutronium fragment cannot cruise through space quietly disguised as a comet. The idea is physically nonsensical. Why then does this simulation get shared and discussed? Because it's terrifying in exactly the right way. It provides a narrative where humanity faces existential danger, not from our own actions, but from cosmic fate. We can't control an interstellar wrecking ball. We can only watch as the solar system unravels. That helplessness is both terrifying and strangely comforting. It removes responsibility. The simulation also offers false precision. Numbers and graphs and orbital plots look authoritative. They carry the aesthetic of science even when the underlying assumptions are fantasy. People trust what looks scientific, even when the science itself is absent. Mainstream orbital dynamics labs haven't sounded alarms because they work with realistic parameters. When you plug in the actual mass estimates for 3I Atlas, the orbital perturbations it causes are negligible. Mercury continues its stable, if slightly eccentric, orbit. Mars stays put. Earth's tilt remains locked by the Moon's stabilizing influence. The solar system carries on as it has for billions of years, indifferent to this brief visitor. But the speculative simulation persists because it speaks to something deeper than physics. It speaks to our fear of cosmic insignificance and our need for grand narratives. What if this is the beginning of something we can't stop? Part 6. What if 3I Atlas isn't solid at all? The distributed mass hypothesis. For centuries we've pictured comets as dirty snowballs, compact lumps of ice and rock tumbling through space. This mental model works well for most objects. You can estimate mass from brightness, measure the size from telescopic observations, and calculate density. But 3I Atlas keeps defying expectations in small ways, and some researchers have begun questioning the fundamental assumption. What if this visitor isn't a single solid body at all? What if the mass is distributed differently than we think, spread across a larger volume or concentrated in unexpected ways? That simple question opens doors to scenarios far stranger than a normal comet. The idea germinated from anomalies in the observational data. Remember that polarimetric study showing unprecedented negative polarization? Light bouncing off 3I Atlas scatters in patterns never observed in other comets or asteroids. Polarization tells us about surface texture and composition. Normal cometary dust produces specific polarization signatures as sunlight reflects off irregular grains. 3I Atlas produces something else entirely. One explanation could be exotic surface materials. Another possibility is that we're not looking at a single solid surface but at a cloud. A swarm of smaller objects gravitationally bound together but separated by significant distances. Light passing through such a distributed mass would scatter differently, producing unusual polarization. Then there's the chemical oddity. Spectroscopic analysis revealed high metal content alongside the expected carbon compounds. One study describes 3I Atlas as potentially metal-bearing, carbonaceous, and pristine. That combination is unusual. Most comets form in the outer regions of stellar systems, where metals remain locked in dust grains or never condensed at all. A metal-rich comet suggests processing by heat or radiation, perhaps exposure to a stellar wind or passage near a dying star. But it could also hint at internal structure we don't understand. Maybe 3I Atlas isn't a homogeneous ice ball. Maybe it's a rubble pile, fragments of different materials loosely bound by mutual gravity, or even a fragment of something larger that broke apart long ago. Some theorists go further. They propose 3I Atlas might be a protoplanetary core fragment, a piece of a planet that never finished forming or was shattered in a collision billions of years ago. Core material would be metal-rich, dense, different from typical cometary composition. If such a fragment wandered through space long enough, it could accumulate an icy mantle from interstellar gas and dust. From the outside, it would look like a comet, outgassing and producing a coma as the ice sublimates. But beneath that disguise, a heavy metallic core hides, carrying far more mass than brightness alone would suggest. This scenario could reconcile the observational contradictions. You get cometary behaviour from the ice mantle, and unexpected mass from the hidden core. The distributed mass hypothesis takes another form in more speculative circles. Imagine 3I Atlas isn't a single object but a cluster, dozens or hundreds of smaller bodies travelling together in a loose formation. From Earth, we see them as one bright source because the distances between individual components are too small to resolve with current telescopes. Each component carries modest mass, but together they add up to something more significant. Such clusters could form when a larger body breaks apart under tidal stress during a close stellar encounter. The fragments remain loosely bound by gravity, but spread across a volume much larger than a solid object of the same total mass. This distributed configuration changes how the object interacts gravitationally with other bodies. Instead of a point source of gravity, you have a complex field with multiple centres. Orbital perturbations from such an object might behave unpredictably. There's even whispered speculation about exotic matter, though this veers into science fiction territory. Could 3I Atlas contain material fundamentally different from normal atoms and molecules? Physicists know that the universe contains far more dark matter than normal matter. We don't understand what dark matter is, but we know it interacts gravitationally. Could an interstellar traveller carry a core of dark matter or some other exotic substance that contributes mass without producing the expected electromagnetic signatures? This would explain why the object seems less massive than its gravitational effects might suggest, but there's absolutely no evidence for this. It exists purely as hypothetical speculation, a way to force the data to fit a preferred narrative. Let's ground this in what we actually observe. Recent infrared observations using space telescopes show 3I Atlas with a coma dominated by carbon dioxide, substantial carbon monoxide, water ice, and silicate dust. This is textbook comet behaviour. The outgassing rates, the coma morphology, the tail structure all match models assuming a relatively standard icy nucleus. When scientists fit these observations to models, they consistently derive masses in the trillion-ton range, nowhere near what would be required for the gravitational mayhem described in earlier scenarios. The comet acts like a comet, not like a disguised planetary core or exotic matter repository. Furthermore, we haven't seen any signs of fragmentation or a distributed structure. If 3I Atlas were a loose cluster, we'd expect to see it spread out as it approached perihelion. The Sun's tidal forces and thermal stresses would pull the components apart, creating a string of objects like Comet Shoemaker-Levy 9 before it hit Jupiter. Nothing like that has been observed. The object maintains a coherent nucleus with a single central condensation. High-resolution imaging doesn't show multiple distinct sources within the coma. All signs point to a single, solid body. The mainstream scientific consensus holds firm. 3I Atlas is an interstellar comet with unusual but not inexplicable properties. The metal content suggests it formed in a different environment than solar system comets, perhaps closer to its parent star where temperatures allowed metals to remain in solid form. The polarization anomaly might reflect unusual dust grain properties shaped by billions of years of cosmic ray bombardment in interstellar space. These are interesting scientific questions worth studying, but they don't require abandoning the basic comet model or invoking exotic physics. So why does the distributed mass hypothesis persist? Partly because it's more interesting. A normal comet is just a cosmic iceberg. A distributed mass object or hidden core or exotic matter fragment is a mystery, something potentially dangerous and unknown. Our minds gravitate toward mystery over mundane explanation. There's also the psychological appeal of hidden threats. The idea that 3i Atlas conceals its true nature plays into fears about things not being what they seem, about dangers lurking beneath innocent surfaces. This resonates with deeper anxieties about trust and knowledge. The hypothesis also thrives in the gaps of our understanding. We don't have perfect knowledge of 3i Atlas. We can't land on it or sample it directly. Our observations come from millions or billions of kilometres away, interpreting reflected and emitted light. That distance leaves room for speculation. When data is ambiguous, competing explanations multiply. The scientific method demands choosing the simplest explanation consistent with observations. That's almost always a standard comet. But human nature often prefers the more elaborate story, especially when it carries implications of danger or discovery. We want 3i Atlas to be special, because that would make our era special, the time when humanity encountered something truly alien and paradigm-shattering. The reality is probably more modest. This is a comet from another star, fascinating in its own right, but not the harbinger of solar system collapse. Unless, of course, there's other evidence we're missing. What about the telemetry from deep space probes? Part 7. The deep space probe telemetry that no one talks about. The outer solar system is a vast, empty place monitored by just a handful of spacecraft. Voyager 1 and 2 continue their journeys into interstellar space, sending back faint signals from beyond the heliosphere. New Horizons, having flown past Pluto, cruises through the Kuiper Belt. A few other probes occupy various positions, their instruments watching the sun from different angles, measuring solar wind and cosmic rays. These spacecraft are marvels of engineering, their positions known to extraordinary precision through radio tracking. Controllers on Earth send signals, the spacecraft echoes back, and the Doppler shift tells us exactly how fast it's moving. Over time, those measurements build into trajectories accurate to meters across billions of kilometers. That precision makes the claims circulating on certain forums all the more intriguing. According to amateur analysts poring over publicly available tracking data, there are anomalies, small ones, easy to miss, but present nonetheless. Around the time 3i Atlas moved through certain regions of space, some claim that spacecraft experienced unmodelled accelerations. These weren't the expected forces: solar radiation pressure pushing on the craft's surface, thermal recoil from heat radiating asymmetrically, or thruster firings programmed into the mission plan. These were residual accelerations, tiny but persistent, that shouldn't be there. The most famous precedent is the Pioneer anomaly, an unexplained sunward acceleration detected in the Pioneer 10 and 11 probes during the late 20th and early 21st centuries. Scientists eventually traced that to thermal radiation from onboard power sources creating subtle thrust. But what if 3i Atlas created a new anomaly, one tied not to the spacecraft, but to external gravitational influence? The official position from mission control teams is silence. No press releases announce unexplained accelerations. No peer-reviewed papers discuss telemetry anomalies correlating with 3i Atlas's trajectory. When anomalies do appear in spacecraft tracking data, they're attributed to routine causes. The spacecraft might vent residual fuel, creating tiny thrust. Solar wind pressure varies, changing the force on the spacecraft. The Deep Space Network antennas sometimes experience interference that corrupts Doppler measurements. All of these happen regularly and are well understood. The absence of official statements about 3i Atlas-related anomalies suggests either they don't exist, or they're too small to matter. But absence of official acknowledgement doesn't satisfy everyone. Some analysts argue that mission telemetry logs are proprietary, shared only within the space agencies and research institutions involved. What gets published publicly is sanitized, smoothed, corrected for known effects. If there were subtle, unexplained accelerations that didn't fit existing models, would space agencies publicize them immediately? Or would they investigate quietly first, trying to understand before making statements that might cause alarm or confusion? The latter seems more likely. which opens space for conspiracy theories. Maybe the anomalies are real, and maybe they're being studied behind closed doors. Let's consider what it would take for 3I Atlas to cause detectable spacecraft anomalies. Gravitational acceleration drops off with the square of distance. At the distances involved, even kilometres of separation, the gravitational pull from a comet mass object would be minuscule. A spacecraft experiences acceleration from the Sun's gravity, vastly overwhelming anything a small interstellar visitor could contribute. To produce measurable effects, 3I Atlas would need to pass extremely close to the spacecraft, within thousands of kilometres, or carry far more mass than observations indicate. There's also the question of what spacetime curvature effects might exist. General relativity predicts that massive objects warp spacetime. Clocks run slower in stronger gravitational fields, and light bends around massive bodies. Could a spacecraft detect spacetime curvature from a passing object through anomalies in its trajectory or timing signals? The answer depends on the mass involved. Earth's gravity produces measurable spacetime curvature that GPS satellites must account for. But Earth is enormously massive compared to a comet. For 3I Atlas to produce detectable curvature, it would need stellar-scale mass. A comet cannot hide that much mass. The gravitational lensing alone would be obvious. Amateur analysts sometimes point to small timing discrepancies in telemetry as evidence. Radio signals travel at light speed, so mission controllers know exactly when to expect replies based on distance. If 3I Atlas's gravity warped space-time along the signal path, the travel time might differ slightly from expectations, but the magnitude of this effect for a comet mass object at relevant distances would be unmeasurable with current technology. We're talking about nanosecond-scale differences, far below the noise floor of the tracking systems. Even if the effect existed, it would be swamped by variations in signal propagation through the solar wind and Earth's ionosphere. The most likely explanation for any claimed anomalies is instrumental. Spacecraft are complicated machines operating in harsh environments. Components age, solar panels degrade, thruster valves leak. Small forces that weren't initially significant become detectable over decades of operation. The Pioneer anomaly remained mysterious for years precisely because the spacecraft was so old and their detailed internal states so uncertain. Modern probes are better monitored, but uncertainty still exists. Attributing small accelerations to known causes requires detailed modelling of every component, every surface, every source of thrust and drag. That work is painstaking and not always perfect. There's also the human factor. People analysing data sometimes see patterns where none exist. Confirmation bias can make you focus on data points that fit your hypothesis while ignoring contradictions. If you believe 3I Atlas is massive and dangerous, you might interpret ambiguous telemetry as supporting evidence. This isn't malicious. It's how human cognition works. We're pattern matchers, and sometimes we match patterns to noise. So where does that leave the deep space probe anomaly claims? In the realm of unverified speculation. Without access to raw telemetry data, and without peer-reviewed analysis from mission teams, we can't evaluate the claims meaningfully. Extraordinary claims require extraordinary evidence. A few forum posts alleging unmodelled accelerations don't meet that standard. Until credible scientists publish findings in reputable journals, the telemetry anomalies remain rumours, intriguing but unsupported. Yet the rumours persist because they feed the larger narrative. If 3I Atlas is a wrecking ball, it should leave evidence everywhere. Spacecraft tracking provides one place to look. The fact that official sources haven't reported anomalies might mean there are none, or it might mean something is being hidden. Conspiracy thinking thrives in that ambiguity. But even if we dismiss spacecraft anomalies, there's still tension in the scientific community itself. The next layer reveals disagreements between experts about long-term consequences. Part 8. The quiet war between ephemeris labs. In the world of celestial mechanics, precision is everything. Ephemerides are tables of planetary positions calculated for past, present and future times. Space agencies use them to navigate probes. Observatories use them to point telescopes. Even your smartphone GPS relies on ephemerides for satellite positions. These tables are generated by specialised labs using complex models that account for gravitational interactions between every significant body in the solar system. The Sun, planets, major moons, largest asteroids, Even solar radiation pressure all contribute. The calculations require supercomputers and careful validation against observations. When something new enters the system, like 3I Atlas, ephemeris labs must decide whether to include it in their models, and if so, what parameters to use. Most major institutions treat 3I Atlas as negligible. The object's estimated mass is too small to affect planetary orbits measurably. NASA's Jet Propulsion Laboratory, which maintains one of the most widely used ephemerids, likely didn't bother including 3I Atlas in calculations beyond verifying it poses no collision risk. Their models use well-constrained masses for all significant solar system bodies. Adding a comet that contributes essentially zero perturbation would be computational waste. The official position is clear. 3I Atlas changes nothing. The planets will continue their orbits as predicted by models developed over decades of refinement. But in smaller research groups and independent dynamics labs, a different picture emerges. Some researchers use 3I Atlas as a test case for exploring uncertainty in mass estimates. What if the standard comet mass assumptions are wrong? What if the object is denser or larger than appearances suggest? They run simulations using extreme parameters, pushing mass estimates to the upper bounds of physical plausibility or even beyond. These aren't predictions. They're sensitivity analyses, exploring how outcomes change under different assumptions. The results can be alarming. With sufficiently high mass, 3I Atlas does perturb orbits. Over decades, those perturbations compound. Simulations show Mercury's orbit destabilizing, Earth's eccentricity increasing, Mars drifting outward. The disagreement isn't about mathematics. Everyone uses the same equations, Newton's laws plus relativistic corrections. The disagreement is about input parameters. Mainstream labs use observationally constrained values. Fringe researchers use speculative values justified by exotic scenarios. It's the difference between modelling reality and modelling what-if scenarios. Both have value, but they serve different purposes. Mainstream models predict what will happen. Speculative models explore what could happen under extreme assumptions. The problem arises when speculative results get shared without context, presented as predictions rather than sensitivity studies. Consider the methodology more closely. Orbital simulations integrate the equations of motion forward in time. You start with current positions and velocities of all bodies, apply gravitational forces, calculate accelerations, update velocities and positions, and repeat for millions or billions of time steps. Tiny errors accumulate, which is why long-term predictions are inherently uncertain. The solar system exhibits chaotic dynamics. Small differences in initial conditions lead to diverging outcomes over millions of years. This is why predicting Mercury's position a billion years from now is impossible, even with perfect current knowledge. The chaos doesn't mean the system is unstable, just that precise long-term prediction is fundamentally limited. When you add a massive object like an extreme assumption 3I Atlas, you introduce perturbations that accelerate the divergence. Resonances between planetary orbits get disrupted. Energy exchanges between planets change. Over time, orbits that were marginally stable become unstable. Mercury, already the most precarious inner planet, is particularly vulnerable. Its orbit is eccentric and its angular momentum low. A series of small kicks from a passing massive body could push it toward chaos. In some simulations, Mercury collides with Venus. In others, it falls into the Sun. In a few runs, it gets ejected entirely. Earth's fate in these scenarios depends on second-order effects. Direct gravitational influence from 3I Atlas is small, even with inflated mass assumptions. But if Mercury or Venus changes orbit significantly, that affects Earth. The inner planets exist in a web of gravitational relationships. Perturb one, and the others respond. Earth's orbit might elongate, increasing eccentricity. That means more variation in solar heating between closest and farthest approach to the Sun. Climate patterns would shift. Ice ages might come more frequently or last longer. The axial tilt might wobble more than normal, again affecting climate. None of this happens instantly. It's a slow drift over decades or centuries. Mars suffers different consequences. It's farther out, less tightly bound gravitationally to the inner system. A perturbation that nudges Mars outward could be amplified by resonances with Jupiter. The giant planet's gravity dominates the outer solar system. If Mars enters a resonance with Jupiter, energy exchanges could pump up Mars's orbital eccentricity or semi-major axis. Over time, Mars migrates outward, its orbit expanding. Surface temperatures drop as solar flux decreases. Any remaining atmosphere freezes out. The planet becomes a frozen, airless rock drifting in the darkness beyond its original orbital zone. Why don't mainstream labs sound alarms about these scenarios? Because they're based on unjustified assumptions. The extreme mass values needed to produce orbital chaos don't match observations. 3I Atlas behaves like a comet with a comet's mass. The coma, the outgassing rates, the brightness curve, all constrain mass to values far below what the chaotic simulations require. Using realistic parameters, the perturbations vanish into the noise. Mercury stays stable. Earth's orbit remains predictable. Mars doesn't migrate. The solar system carries on as it has for billions of years. Yet the speculative simulations circulate online, shared in forums and social media. They're presented with graphs and orbital plots that look authoritative. Few viewers have the background to evaluate the assumptions underlying the results. The simulations look scientific, so they're treated as scientific, even when they're essentially fiction. This creates a public perception gap. Non-experts see contradictory claims. Some sources say 3I Atlas is harmless. Others show simulations of planetary ejection and orbital collapse. Who to believe? The tendency is to assume the truth lies somewhere in between, that maybe there's some risk even if not as extreme as worst-case scenarios suggest. But the reality is more binary. Either 3I Atlas has the mass to perturb orbits or it doesn't. Observations strongly indicate it doesn't. The quiet war between ephemeris labs isn't really a war. It's a misunderstanding amplified by poor science communication. Mainstream researchers focus on predictions using best-fit parameters. Fringe researchers explore extreme scenarios for completeness or sensationalism. Both produce valid work within their contexts, but mixing them creates confusion. The public deserves clarity. 3I Atlas, as currently understood, poses no orbital threat. The speculative scenarios require assumptions contradicted by all available evidence. But if orbits are stable, what about Earth's rotation? Part 9. The axis flip and climate reversal models. No one wants released. Imagine waking up one day to find the seasons reversed. Summer becomes winter, winter becomes summer. The sun rises in the west and sets in the east. Antarctica melts while Greenland becomes habitable. This isn't the plot of a science fiction novel. It's the premise of speculative models that link 3I Atlas to Earth's rotational stability. These models predict not orbital catastrophe, but something subtler and potentially more insidious. A gradual shift in Earth's axial tilt that reorganizes climate zones over decades, rendering agriculture impossible, displacing billions, and collapsing civilization as we know it. Earth's rotation axis tilts at 23.5 degrees relative to the orbital plane. This tilt causes seasons. When the northern hemisphere tilts toward the sun, it's summer there and winter in the south. 6 months later, the situation reverses. The tilt has remained stable for millions of years, locked in place by the gravitational influence of the moon. Our satellite acts as a gyroscopic stabilizer, damping wobbles and preventing large tilt variations. Without the moon, Earth's axis would wander chaotically over relatively short timescales, causing wild climate swings. With the moon, we get predictable, moderate tilt variations called Milankovitch cycles that operate over tens of thousands of years. The speculative models propose that 3I Atlas could destabilize this system. The mechanism involves torque, a rotational force. When a massive object passes near Earth, it doesn't just pull on the planet's center of mass, it pulls more strongly on the near side than the far side. If Earth's mass is distributed symmetrically, such as with ice caps concentrated at the poles, this differential pull can create a torque on the rotation axis. The torque tries to twist Earth's axis toward or away from the passing object. Usually such torques are minuscule and quickly damped by Earth's rotational inertia and the moon's stabilizing influence. But if the passing object were massive enough and close enough, the torque could be significant. The models assume 3I Atlas carries far more mass than observation support. They place it on a trajectory that brings it closer to Earth than actually occurred. With these inflated parameters, the gravitational torque becomes substantial. Earth's axis begins to wobble. Over years, the wobble grows as repeated passes. Wait, 3I Atlas only passes once, so the models instead invoke a prolonged gravitational interaction as the object slowly transits the inner solar system over months. The torque acts continuously during that time, nudging the axis bit by bit. After 3i Atlas departs, the axis doesn't immediately return to normal. The Moon tries to restore stability, but the perturbation was large enough that the axis settles into a new equilibrium, tilted several degrees differently than before. A tilt change of just 5 degrees reorganises the entire planet's climate. Regions that were temperate become Arctic. Polar areas receive more summer sunlight and warm dramatically. The Hadley cells, atmospheric circulation patterns driven by solar heating differences between equator and poles, shift. Monsoons that brought seasonal rain to India and Southeast Asia fail or move to different latitudes. The Sahara Desert might see regular rainfall while the Amazon dries out. Ocean currents, which depend on temperature and salinity gradients, reorganize. The Gulf Stream could weaken or redirect, plunging Europe into harsh winters. The Antarctic circumpolar current might alter, changing how heat distributes around the southern hemisphere. Agricultural consequences would be catastrophic. Modern farming depends on predictable weather and consistent growing seasons. Crops are bred for specific climate zones. When those zones shift, crops fail. Moving agriculture to new regions takes decades. You need to clear land, develop infrastructure, breed new crop varieties adapted to the changed conditions. During the transition, food production collapses, famine spreads, populations migrate toward regions that remain habitable. Conflicts erupt over resources, water, arable land. The geopolitical order fractures. Nuclear-armed states facing collapse might lash out. The scenario spirals into apocalypse not from the tilt change itself, but from humanity's inability to adapt quickly enough. This makes for compelling drama. But does it have any basis in physics? Let's examine the forces involved. The torque on Earth's axis depends on 3 factors: the mass of the perturbing object, its distance from Earth, and Earth's asymmetry in mass distribution. Calculate the torque by multiplying the gravitational gradient by Earth's moments of inertia and the angular displacement. For a comet mass object at 1.8 astronomical units, the torque is vanishingly small. Even with inflated mass estimates, you'd need to bring 3i Atlas much closer, within a few million kilometres, to generate meaningful torque. That didn't happen. There's also the Moon to consider. The Moon's stabilising torque on Earth's axis is enormous compared to any transient visitor. The Moon is close, just 384,000 kilometres away, and massive, more than 7 times 10 to the 22nd kilograms. Its gravitational influence on Earth's axis swamps any contribution from a distant comet. For 3i Atlas to overcome the Moon's stabilisation, it would need to be not just massive, but absurdly massive, approaching planetary scale. No observational evidence supports that. Furthermore, we monitor Earth's rotation incredibly precisely. International services track the planet's rotation rate, the position of the rotation poles, and variations in both. These measurements reach sub-millisecond precision. If external gravitational torques were significantly affecting Earth's axis, we'd see it in the data as anomalous polar motion, or changes in the length of day. No such anomalies have been reported in connection with 3i Atlas's passage. Earth's rotation continues behaving exactly as expected, based on well-understood causes like atmospheric angular momentum, exchange, tidal friction, and post-glacial rebound. The Milankovitch cycles provide a useful comparison. These natural variations in Earth's orbital eccentricity, axial tilt, and precession operate over tens of thousands of years. They're driven by gravitational interactions with Jupiter and Saturn and the slow migration of Earth's orbit. The tilt variation is only about 2 degrees over 41,000 years. Climate responds to these gentle changes, pacing ice ages and interglacials. The speculative 3i Atlas models compress similar or larger changes into decades, 1,000 times faster. The physics doesn't support such rapid shifts without correspondingly extreme forcing. So why do these models persist? They tap into existential climate anxiety. People are already worried about anthropogenic climate change, rising seas, extreme weather. The idea that a cosmic visitor could trigger even more drastic climate shifts adds another layer of dread. It's also a form of fatalism. If 3i Atlas caused the axis to shift, there's nothing we could have done. The disaster is external, cosmic, inevitable. That removes guilt and agency, which can be psychologically comforting even as the scenario itself is terrifying. We become victims of the universe rather than authors of our fate. The axis flip models also play into apocalyptic narrative traditions. Every culture has stories of world-ending events, floods, fires, skies falling. The modern scientific framing, Earth's axis tilting, planetary climate collapsing, feels like an update to ancient myths. It satisfies the same psychological needs, providing a grand narrative of destruction and renewal. The fact that the scenario is implausible doesn't diminish its emotional power. If anything, the technical veneer makes it more compelling. It's not mythology, it's a climate model with equations and parameters. That gives it authority in a scientific age, even when the science underneath is deeply flawed. But if the axis isn't flipping and the orbits aren't chaotic, is there one final doomsday scenario to consider? Part 10. The 50-year ejection scenario and the Artemis Protocol leak. The rumour first appeared on an obscure forum dedicated to space policy analysis. Someone claiming insider knowledge at a major space agency posted a cryptic message about continuity planning. The post mentioned something called the Artemis Protocol, a classified framework allegedly developed to ensure human survival in the event of planetary ejection. According to this anonymous source, deep within mission planning documents for lunar bases and Mars colonies, there exists evidence that agencies are preparing not just for exploration but for evacuation. The claim is bold and specific. Earth's orbit will destabilize over the next 50 years, gradually shifting outward until the planet escapes the sun's gravitational grip entirely. We will become a rogue world, tumbling through interstellar space, and someone, somewhere, knows this is coming. The official position from space agencies is unambiguous. 3i Atlas poses no threat to Earth. NASA's public statements emphasize that the object is on an unbound hyperbolic trajectory, passing through the solar system once and never returning. Its mass is too small to affect planetary orbits. The closest approach to Earth was 1.8 astronomical units, far beyond any distance where gravitational interaction would matter. The European Space Agency echoes this assessment. So does every major astronomical institution. If there were genuine concern about orbital destabilization, the scientific community would be united in raising alarms. Instead, the alarm comes only from fringe sources and anonymous leaks. Yet the Artemis Protocol narrative persists because it weaves together several threads into a compelling conspiracy. First, there's the timing. Space agencies are indeed accelerating plans for permanent lunar bases and crewed Mars missions. The Artemis program aims to establish a sustained human presence on the Moon by the 2030s. SpaceX and other private companies are developing vehicles for Mars colonization. These efforts are publicly justified as exploration, resource utilization, and expansion of human civilization. But what if there's another motive? What if these off-world installations are actually lifeboats? Infrastructure being positioned now so that when Earth's orbit begins its final decay, a portion of humanity can survive elsewhere. The leaked documents, if they exist, supposedly contain reference to multi-decade infrastructure timelines, deep underground shelters on the Moon and Mars, cryogenic seed banks, and spacecraft designs for interstellar travel. The anonymous source claimed to have seen PowerPoint presentations with titles like long-term continuity planning and planetary evacuation scenarios. These weren't publicly available. They were embedded in classified annexes to routine mission plans. The source suggested that a small group of scientists and administrators know the truth about 3i Atlas, that its actual mass is far greater than publicly admitted, and that orbital modelling shows inevitable ejection beginning in the 2030s. Let's examine what Earth ejection would actually entail. Planets orbit stars because they're gravitationally bound. Escaping that bond requires achieving escape velocity, about 42 kilometers per second at Earth's current orbital distance. For Earth to leave the solar system, something must add enough energy to accelerate the planet to that speed. The energy required is staggering, on the order of 10 to the 33 joules. That's millions of times more energy than humanity has consumed in all of history. Where would that energy come from? In the speculative scenarios, it comes from gravitational interactions with 3i Atlas and subsequent resonance effects with other planets. The mechanism supposedly works like this. 3i Atlas's passage perturbs Earth's orbit slightly, increasing eccentricity and semi-major axis by small amounts. That perturbation changes Earth's orbital period and its gravitational interactions with Venus and Jupiter. Over decades, resonances develop. Every few orbits, Earth passes Venus or Jupiter at similar points in space, and they exchange orbital energy. If the timing works out unfavourably, Earth gains energy in each exchange, pumping up its orbit like a swing being pushed at the right moment. Over centuries, the orbit expands and elongates, until eventually Earth's aphelion, its farthest point from the Sun, extends beyond any planet's influence. At that point, interactions with passing stars or the galactic tide could give Earth the final kick needed to escape. This scenario is theoretically possible in chaotic n-body systems. Simulations of planetary systems sometimes produce ejections over long timescales, but the initial perturbation required to start the process is substantial. A comet-mass object cannot provide it. You'd need something planet-sized passing through the inner solar system. That would be immediately obvious. Such an object would perturb every planet, asteroid, and artificial satellite. It would dominate the sky, visible to the naked eye for weeks or months. The fact that we observed 3I Atlas only with telescopes tells us it's not remotely massive enough to trigger ejection scenarios. The Artemis Protocol leak also fails basic logic tests. If space agencies knew Earth would be ejected in 50 years, why continue with business as usual? Why not redirect all resources toward evacuation infrastructure? Why maintain the fiction that everything is fine? The scale of the response would be impossible to hide. You'd need to build not just lunar bases, but entire self-sustaining colonies capable of housing millions. You'd need massive spacecraft, agricultural systems, energy generation, all deployed off-world within decades. The industrial effort would rival World War II mobilization. Keeping that secret would be impossible. Furthermore, consider the ethics. If a small group of officials knew about impending planetary ejection, would they really keep it secret from the global population? Some might argue yes, to prevent panic. But the moral calculus is complex. People deserve to know existential threats. They deserve the chance to prepare, say goodbye, make choices about how to spend their remaining time. Suppressing that information would be one of the greatest crimes in history. While conspiracies do occur, they rarely involve thousands of people across dozens of countries maintaining perfect silence about information this significant. The psychological appeal of the Artemis Protocol narrative is clear. It provides a hidden truth that explains confusing events. Why are governments suddenly interested in space colonization? Not for exploration, but for survival. Why are billionaires building rockets? Not for profit, but to escape. The conspiracy offers simple answers to complex questions. It also validates fears about transparency and trust. Many people already suspect governments hide important information. The Artemis Protocol confirms that suspicion, offering concrete evidence, or at least the claim of evidence, that we're being lied to about cosmic dangers. There's also the appeal of being in the know. Sharing and discussing leaked information creates a sense of insider status. You're one of the few who understands what's really happening, while the masses remain ignorant. That feeling is powerful, addictive even. It transforms anxiety into a kind of superiority. You're not scared because you're foolish. You're scared because you're informed, because you see what others miss. This dynamic drives much conspiracy thinking. The content almost doesn't matter as much as the social and psychological function it serves. But let's entertain the possibility for a moment. Suppose the Artemis Protocol is real. Suppose a small group does know that Earth will be ejected and is quietly preparing. What would that actually look like? You'd expect to see unusual budget allocations, strange mission priorities, classified programs with vague descriptions. You'd see recruitment of specialists in closed life support systems, long-duration spaceflight medicine, psychology of isolated populations. You'd see construction of deep underground facilities justified as research stations or military installations. You'd notice an acceleration of seed banking, data archiving, and cultural preservation efforts. Some of these things are indeed happening, but they're all explainable by conventional motives preparing for climate change, asteroid impacts, nuclear war, pandemics. All the disasters we know are plausible. The final nail in the Artemis Protocol's coffin is the science itself. We have decades of precise orbital data for every planet. We have sophisticated models that predict positions years in advance. If Earth's orbit were destabilizing, we'd see it in the data now. Orbital mechanics doesn't hide its effects for decades before suddenly manifesting. The perturbations compound gradually, becoming visible early on. Astronomers around the world monitor planetary positions constantly. Any anomaly would be detected by dozens of independent observers. The idea that only a secret group knows about orbital destabilization, while the broader astronomical community remains oblivious, defies credibility. So where does that leave us? The Artemis Protocol is almost certainly fiction, either deliberate misinformation or the product of misunderstanding and paranoia. The 50-year ejection scenario lacks any scientific basis given what we know about 3I Atlas. Earth will remain in its orbit circling the Sun for billions of years until the Sun itself expands into a red giant and engulfs the inner planets. That's our actual long-term fate, not ejection triggered by an interstellar comet. But the persistence of these narratives tells us something important. We live in an age of cosmic anxiety. The universe feels less stable, less predictable than it once did. We're discovering that interstellar visitors exist, that our solar system is permeable, that cosmic events we barely understand are happening all around us. In that context, apocalyptic scenarios flourish. They give shape to formless dread. They provide narratives where the uncertain becomes certain, even if the certainty is catastrophic. Perhaps the real story isn't about what 3I Atlas did, but about what its appearance reveals about us. We're a species awakening to cosmic vulnerability, and we don't yet know how to process that awareness without spiraling into fear. Part 11, 2025. Discoveries. 3I Atlas and the New Age of Interstellar Visitors. The year 2025 may be remembered as the moment humanity realized we're not alone in a quiet cosmic neighborhood. 3I Atlas isn't just a curiosity. It's the third confirmed interstellar object to pass through our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. 3 confirmed visitors in 8 years suggests these objects aren't rare flukes. They're regular occurrences, perhaps dozens or hundreds passing through every year that we simply miss because they're faint or fast or angled wrong for detection. Our solar system sits within a galaxy containing hundreds of billions of stars. Each star likely formed with a debris disk, chunks of rock and ice that never coalesced into planets. When stars pass near each other, or when planets gravitationally scatter material, some of those chunks get ejected into interstellar space. They wander the galaxy for millions or billions of years until occasionally one passes through another star system. We're starting to catch them. What makes 3I Atlas particularly fascinating is its composition. The James Webb Space Telescope and other instruments turned their gaze toward this visitor, gathering infrared spectra that reveal chemical fingerprints. The data shows a coma dominated by carbon dioxide, with substantial carbon monoxide, water ice and silicate dust. This combination is unusual. Most comets in our solar system have water as the primary volatile, with carbon dioxide and carbon monoxide as secondary components. 3I Atlas flips that ratio. Carbon dioxide dominates, water is secondary. That suggests it formed in a colder environment than typical solar system comets, perhaps farther from its parent star where carbon dioxide could condense, but water remained mostly gaseous. There's more. Detailed spectroscopic analysis reveals signatures of complex organic molecules, carbon-based compounds that could include things like methanol, formaldehyde, and possibly even more elaborate structures. Some popular media coverage breathlessly suggests these organics could be precursors to life, that 3I Atlas might be delivering the building blocks of biology from another stellar system. The reality is more nuanced. Organic molecules form easily in space through non-biological chemistry. Ultraviolet radiation, cosmic rays, and simple chemical reactions in cold molecular clouds produce a whole zoo of carbon compounds. Finding organics on a comet doesn't imply life. It just confirms that basic chemistry operates the same way everywhere in the galaxy. But there's something genuinely intriguing in the spectroscopic data. 3I Atlas shows evidence of metal content, possibly native iron or nickel mixed with the ice and dust. This is highly unusual for comets, which typically contain only trace metals locked in mineral grains. Substantial metal content suggests processing by heat or radiation that our solar system comets didn't experience. One hypothesis proposes that 3I Atlas formed closer to its parent star, in a region where temperatures were high enough for metals to remain in solid form, then got ejected outward and eventually out of the system entirely. Another idea suggests the object is a fragment of something larger, perhaps a protoplanetary core that shattered in a collision and has been wandering interstellar space ever since. Recent research also points to galactic cosmic ray irradiation. When objects drift through interstellar space for millions of years, they're bombarded constantly by high-energy particles, cosmic rays originating from supernova remnants and other violent events. This radiation alters surface chemistry, breaking apart molecules and creating new compounds. It also darkens surfaces, producing a radiation crust rich in organic tars and altered minerals. 3I Atlas's outer layers may show this signature, a record of its long journey through the galaxy before arriving here. If confirmed, that would tell us something profound about the timescales involved. This object has been travelling for a very long time, possibly since its parent star system was young. The implications extend beyond chemistry. Each interstellar visitor offers a glimpse into planetary formation processes around other stars. We can study exoplanets, planets orbiting distant stars, but we can't examine their composition directly. They're too far away, too faint. Interstellar comets bring samples to us. By analysing their chemical makeup, we learn about conditions in other stellar systems. Were those systems similar to ours, or radically different? Did they have the same inventory of elements, or were they enriched or depleted in certain species? 3I Atlas suggests diversity. Not every planetary system looks like the Sun's. This revelation matters for astrobiology. If planetary systems vary widely in composition, then the conditions for life might exist in unexpected places, or fail to appear where we'd expect them. Water-rich worlds like Earth might be rarer than we thought, while carbon dioxide-rich worlds could be common. Life as we know it requires liquid water, but some researchers speculate about alternative biochemistries based on other solvents. 3I Atlas's carbon dioxide dominance makes you wonder about frozen worlds, where carbon dioxide takes the place water holds here, acting as a medium for chemistry and energy transfer. The discovery of these interstellar visitors also forces us to rethink solar system defence. For decades, planetary defence focused on asteroids and comets native to our system. We've catalogued most large near-Earth asteroids. We track comets that might threaten us. But interstellar objects arrive with little warning, moving fast on unpredictable trajectories. 3I Atlas was detected months before perihelion, giving us time to observe it. But a smaller object, or one coming from a different angle, might not be spotted until too late. If an interstellar asteroid on a collision course appeared with only weeks of warning, we'd have no time to mount a deflection mission. The infrastructure for planetary defence assumes decades of lead time. Interstellar impactors don't grant that luxury. This isn't just theoretical. The fact that we've detected 3 interstellar objects in 8 years, despite our limited sky coverage, implies many more pass through undetected. Some estimates suggest dozens per year. Most are small, harmless, but occasionally a large one will arrive. The statistical odds of an interstellar impact are low, far lower than the threat from native asteroids. But they're not zero. And unlike native objects, we can't track interstellar visitors in advance. They're invisible until they're already here, blazing through the inner solar system at hyperbolic speeds. The scientific community is responding by developing better detection systems. Next-generation sky surveys will scan larger fractions of the sky more frequently, catching fast-moving objects earlier. Improved computational tools will allow real-time identification of hyperbolic trajectories, flagging interstellar visitors immediately. Space agencies are discussing rapid response protocols, missions that could launch on short notice to intercept and study these objects up close. The goal is to transform interstellar visitors from surprises into anticipated events, objects we detect, characterize, and prepare for. But detection is only half the challenge. Understanding what we're seeing requires new frameworks. 1I/Oumuamua famously defied easy categorization. It showed no coma, no tail, yet accelerated slightly as it left the solar system, behavior attributed to outgassing despite the lack of visible activity. 2I/Borisov looked like a normal comet, familiar and comforting. 3I Atlas falls somewhere in between, cometary but chemically odd. Each visitor forces us to expand our definitions and question assumptions. The universe contains more variety than our solar system prepared us for. 2025 also brought advances in understanding how these objects form and get ejected. simulations of planetary system evolution show that gravitational scattering is common. When giant planets migrate inward or outward during a system's youth, they fling countless smaller bodies into interstellar space. Every star likely contributes to a galactic population of wandering debris. Some researchers estimate trillions upon trillions of these objects drift between the stars, leftovers from billions of planetary systems. We're only now starting to sample that population. The more we look, the more we'll find. And each discovery teaches us something new about the galaxy's hidden architecture, the vast web of matter connecting stars across light years of emptiness. But these visitors aren't the only cosmic surprises of 2025. New instruments are also revealing strangeness closer to home. Part 12. Quantum gravimeters, space-time fluctuations and wormhole dreams. In late 2025, a research group in Europe announced something peculiar. Their quantum gravimeter, an instrument so sensitive it detects variations in gravitational acceleration down to a billionth of Earth's surface gravity, recorded anomalous fluctuations. These weren't the expected signals from Earth tides, atmospheric pressure, changes, or groundwater movement. These were brief, localized dips and spikes in the gravitational field that appeared without obvious cause and vanished within minutes. The data came from multiple sites, instruments separated by hundreds of kilometers, but showing similar patterns around the same times. The researchers published preliminary findings cautiously, emphasizing the need for further investigation. But the internet leaped to conclusions. Could these be ripples in space-time itself? Could 3i Atlas have left gravitational echoes, distortions propagating through the fabric of reality? Quantum gravimeters represent a leap in measurement technology. Traditional gravimeters use springs or falling masses to sense gravitational acceleration. They're precise, but limited. Quantum gravimeters use matter waves, exploiting the wave-particle duality of atoms. A cloud of ultra-cold atoms is split and recombined using laser pulses. The interference pattern that emerges depends on the gravitational field the atoms experienced. Because quantum interference is exquisitely sensitive, these instruments detect gravitational changes invisible to classical devices. They're used for geology, mapping underground density variations, finding hidden voids or ore deposits. They're also employed in fundamental physics research, testing theories of gravity and searching for exotic phenomena. The anomalies reported in 2025 didn't fit known categories. They weren't large enough to indicate massive underground structures suddenly appearing and disappearing. They weren't correlated with seismic activity, which produces measurable gravity changes as rock masses shift. They weren't tied to atmospheric phenomena, which can alter local gravity by changing air density overhead. The fluctuations seemed genuinely mysterious, at least initially. Some researchers speculated about quantum gravity effects, fleeting distortions in space-time predicted by theories attempting to unify general relativity and quantum mechanics. Others wondered if the instruments were detecting gravitational waves, ripples from distant cosmic events that somehow produced localized anomalies. The connection to 3i Atlas emerged from timing. The fluctuations clustered around dates when the interstellar visitor was near perihelion, or crossing certain heliocentric longitudes. That correlation, while intriguing, doesn't prove causation. Many things happen simultaneously without being related. The human mind excels at finding patterns, even in random data. When you're looking for connections, you'll find them whether they exist or not. Still, the possibility tantalized. What if 3i Atlas carried enough mass to warp spacetime measurably? What if its passage left gravitational scars that sensitive instruments could detect? Let's ground this in physics. Spacetime curvature depends on mass-energy density. Earth curves spacetime enough that clocks at different altitudes tick at different rates, a measurable effect exploited by GPS. The Sun curves spacetime far more, bending light from distant stars as it passes nearby, an effect observed during solar eclipses and used to confirm general relativity. For 3i Atlas to produce detectable spacetime curvature on Earth's surface, it would need to be extraordinarily massive or pass extraordinarily close. Neither condition holds. The object passed at 1.8 astronomical units, with a mass consistent with a comet. The resulting spacetime curvature would be negligible, far below the detection threshold of even quantum gravimeters. Consider the numbers. Gravitational potential drops off with distance. At Earth's surface, The gravitational potential from the Sun produces time dilation of about 1 part in 10 to the 8th. That's measurable over long baselines with atomic clocks. 3I Atlas, at its closest, was more than 200 million kilometres away with a mass millions of times smaller than the Sun. Its contribution to Earth's gravitational potential would be unmeasurable, lost in the noise from Earth's own gravity and the Sun's overwhelming influence. The gravimeter anomalies, if real, cannot be attributed to 3I Atlas without invoking physics that contradicts everything we know. There's another interpretation, though, one that doesn't require rewriting general relativity. Perhaps the anomalies aren't real gravitational fluctuations, but instrumental artifacts. Quantum gravimeters are temperamental. They require ultra-cold atoms, stable lasers, precise timing, and isolation from vibrations and electromagnetic interference. A passing truck, a temperature shift, a stray magnetic field, all can introduce spurious signals. The fact that multiple sites showed similar anomalies might reflect common environmental factors, like a regional weather pattern or geomagnetic disturbance, rather than a genuine gravitational phenomenon. Careful analysis usually reveals these prosaic explanations, yet some researchers push for more exotic possibilities. What if the anomalies indicate dark matter? The universe contains far more dark matter than normal matter, but we don't know what dark matter is. It interacts gravitationally but not electromagnetically, making it invisible except through its gravitational effects. Could clumps of dark matter pass through Earth occasionally, producing brief gravitational anomalies? This idea has been explored before. Some models suggest dark matter exists in streams or lumps rather than being smoothly distributed. If such a lump passed through our neighbourhood, quantum gravimeters might detect it. But the expected signal would be different from what was reported, more gradual and longer lasting. Then there are the truly speculative ideas. Micro-wormholes, shortcuts through space-time predicted by general relativity but never observed, might produce gravitational anomalies if they formed and evaporated near Earth. Primordial black. Holes, hypothetical remnants from the early universe, could pass through the solar system and warp space-time detectably. Some fringe theorists even suggest the anomalies are evidence of parallel universes briefly touching ours. These ideas are fun to contemplate but entirely unsupported by evidence. They exist at the boundary between science and science fiction, places where imagination runs wild, unconstrained by data. The proper scientific response to the gravimeter anomalies is skepticism paired with curiosity. Extraordinary claims require extraordinary evidence. Anomalies in sensitive instruments require exhaustive investigation of mundane causes before invoking exotic physics. The research groups involved are doing exactly that, checking calibration, ruling out environmental factors, comparing data from different sites and times. If, after all that, the anomalies persist and resist conventional explanation, then and only then should we entertain more radical ideas. Science advances through careful, methodical work, not by leaping to conclusions. What the gravimeter episode reveals is how ready we are to connect isolated phenomena to larger narratives. 3I Atlas becomes a convenient explanation for anything unusual happening in 2025. Earthquake warnings in Japan. Must be the comet. Internet glitches. The comet. Solar flares. The comet. Gravity anomalies. Also the comet. This reflects a cognitive bias called apophenia, seeing meaningful connections in unrelated events. It's the same mechanism that produces conspiracy theories. When the world feels uncertain and overwhelming, we grasp for simple explanations that tie everything together. 3I Atlas serves that psychological need even when the actual evidence is weak or absent. But here's a thought. Even if 3I Atlas isn't causing gravitational anomalies, the fact that we have instruments sensitive enough to look for them is itself remarkable. We live in an age where humanity can measure space-time curvature with extraordinary precision, where we detect gravitational waves from black hole collisions billions of light years away, where we probe the fabric of reality at scales previously inaccessible. That's profound. Whether or not 3I Atlas left gravitational fingerprints, the search for those fingerprints demonstrates how far our capabilities have evolved. We're no longer passive observers of the cosmos, we're active investigators, equipped with tools that would have seemed like magic a generation ago. Perhaps the real story isn't about what we found, but about what we're now able to look for. And in 2025, those tools extended beyond gravity into realms of prediction and foresight. Part 13. AI-driven solar and stellar prediction. Breakthroughs. 2025 brought another breakthrough that received less attention than it deserved. An artificial intelligence system, trained on decades of solar observation data, successfully predicted a major X-class flare 3 weeks before it erupted. The prediction wasn't vague, something like a flare might occur soon. It specified the active region, the approximate timing within a 2-day window, and the estimated intensity. When the flare actually occurred, matching the prediction closely, it marked a turning point. For the first time, humanity demonstrated the ability to forecast solar activity with meaningful accuracy and lead time. If we can predict solar chaos, perhaps we can eventually predict other cosmic hazards. Solar flares result from magnetic reconnection, a process where tangled magnetic field lines in the Sun's atmosphere snap back into simpler configurations, releasing enormous energy. The physics is understood conceptually but incredibly complex in detail. Magnetic fields in the solar corona are shaped by plasma motions deep in the Sun's interior. Those motions are turbulent, chaotic, and difficult to model. Predicting when and where reconnection will occur requires tracking the evolution of magnetic structures across the Sun's surface and extrapolating how they'll behave in 3-dimensional space above. Traditional physics-based models struggle with this. They capture the general behavior but miss the specifics. Artificial intelligence offers a different approach. Instead of modeling the underlying physics explicitly, machine learning systems find patterns in historical data. The AI was trained on thousands of images showing the Sun's magnetic field over multiple solar cycles. It learned to recognize configurations that precede flares, subtle patterns in field strength and topology that human observers might miss. When presented with current data, the AI identifies those patterns and predicts whether a flare is likely, when it might occur, and how intense it could be. The system doesn't understand why the patterns matter. It just knows they correlate with future flares. The successful prediction sent ripples through the solar physics community. If AI can forecast flares, what else can it predict? Could similar systems warn of coronal mass ejections with enough lead time to protect satellites and power grids? Could they forecast geomagnetic storms that threaten astronauts and disrupt communications? The answer appears to be yes. Several research groups are now developing AI-based space weather prediction systems. The goal is real-time forecasting, a continuous stream of warnings about solar activity with hours or days of lead time. This technology has obvious practical applications. Solar storms can damage satellites, disrupting GPS, communications, and reconnaissance. They can induce currents in power grids, potentially causing transformer failures and blackouts. They expose astronauts and airline crews to elevated radiation levels. Being able to predict these events allows operators to take protective measures. Satellites can be put into safe mode, power grids can be reconfigured. To minimize damage, flights can be rerouted and astronauts can shelter. The economic and safety benefits are substantial, but there's a darker side to consider. If AI can predict solar flares, governments and institutions will want to control that information. Space weather forecasting could become classified, restricted to those with security clearances. Early warnings might be shared with military and critical infrastructure operators, but withheld from the public. The justification would be preventing panic or protecting strategic advantage. Yet this creates asymmetries. Those with access to predictions can prepare. Those without suffer the consequences. The technology that should democratize safety instead concentrates power. There's also the risk of false positives and false negatives. No prediction system is perfect. The AI might forecast a flare that doesn't occur, causing unnecessary disruptions as systems shut down preemptively. Or it might miss a flare, leaving populations unprotected. How do we calibrate trust in these systems? How do we communicate uncertainty to the public? These are social and political questions as much as technical ones. The breakthrough in prediction creates new responsibilities. The AI prediction story also connects to 3i Atlas in a subtle way. If we're entering an era where solar activity, seismic events, atmospheric phenomena, and even asteroid impacts can be predicted using machine learning, then the cosmos becomes less mysterious, more manageable. But that assumes the AI systems are trained on representative data. What happens when something unprecedented occurs, something outside the training set? 3i Atlas is precisely that kind of event. An interstellar visitor, whose properties and effects might not match anything in the historical record. AI trained on solar system comets might completely misunderstand an interstellar object. Predictions could fail catastrophically because the system encounters a situation it was never designed to handle. This reveals a fundamental limitation of machine learning. These systems excel at interpolation, making predictions within the range of their training data. They struggle with extrapolation, handling situations significantly different from what they've seen. As we encounter more cosmic anomalies, more unexpected phenomena, the AI tools we're building might become liabilities rather than assets. We'll trust them, rely on them, and then be blindsided when they fail in the face of genuine novelty. 3i Atlas, whether or not it's dangerous itself, serves as a reminder that the universe contains surprises. No amount of historical data prepares you for something fundamentally new. Yet the optimistic view is that AI prediction represents humanity's growing maturity. We're moving from reactive to proactive, from passive victims of cosmic events to active managers of risk. That's progress, even if imperfect. The solar flare prediction is just the beginning. Future systems might forecast asteroid trajectories decades in advance, identify stellar systems likely to send interstellar visitors our way, or even detect gravitational wave events before they peak. We could live in a world where cosmic hazards are anticipated and mitigated as routine. The question is whether we'll use that capability wisely, or whether it'll lull us into complacency. There's something almost ironic about the timing. The same year we develop AI to predict solar chaos is the year an unpredictable interstellar visitor passes through. It's as if the universe is reminding us that no matter how sophisticated our tools become, surprises will always exist. 3i Atlas might be benign, just a comet from another star. But its appearance highlights the limits of prediction and control. We can forecast some things, prepare for others, but we can't anticipate everything. The cosmos is too vast, too complex, too full of variables we don't understand, and in 2025 another event drove that lesson home even more dramatically. Part 14. The 2025 Vacuum Decay. Scare, Fear, Physics and Media Hysteria. Early in 2025, a preliminary result from a particle physics experiment briefly suggested something terrifying. The data hinted at possible vacuum instability, a scenario where the fundamental quantum fields pervading the universe might not be in their lowest energy state. If true, this would mean our universe exists in a false vacuum, a metastable condition that could decay catastrophically at any moment. The decay would create a bubble of true vacuum expanding at the speed of light, annihilating everything it touches. No warning, no escape, just instant obliteration as the laws of physics themselves rewrite. The story exploded across media outlets. Headlines screamed about the end of the universe, social media filled with panic and gallows humour. Then, within days, the anomaly was traced to detector noise. The vacuum was fine, but the episode revealed how easily frontier physics morphs into apocalyptic narrative. Vacuum decay is a real concept in quantum field theory. The Higgs field, which gives particles mass, sits at a particular energy level. If calculations show that a lower energy state exists, then our current state is metastable, like a ball balanced on a hill rather than resting in a valley. Eventually, quantum tunneling could cause a transition. A region of space would suddenly flip to the true vacuum, and that region would expand at light speed, consuming the universe. The physics is sound, the implications genuinely catastrophic, but whether our vacuum is actually metastable depends on precise measurements of particle masses and field interactions, measurements we don't yet have with sufficient accuracy. The 2025 scare began with a data analysis glitch. An experiment measuring rare particle decays saw an unexpected energy signature. Someone ran simulations suggesting this signature could indicate vacuum instability. They presented preliminary findings at a conference, emphasizing uncertainty and the need for verification. But a journalist in attendance understood only the dramatic implications and wrote a sensational article. Other outlets picked it up, amplifying the fear. Within hours, vacuum decay was trending globally. People asked if the universe could end tomorrow. Some claimed it already had. The bubble of true vacuum was expanding toward us right now. We just didn't know it yet because light from the decay front travels at the same speed as the destruction itself. That particular horror is unavoidable. If vacuum decay happens elsewhere in the universe and propagates toward us, we won't see it coming. The first and last sign will be simultaneous annihilation. The physics community moved quickly to correct the record. Multiple groups analysed the same data independently and identified the error. The energy signature was instrumental noise, a detector artifact, not a sign of fundamental instability. The vacuum remained stable, at least as far as current measurements could determine. Media outlets issued corrections, some prominently, others buried. The panic subsided, but the damage lingered. Trust in scientific communication eroded a little more. People remembered the fear more than the correction. The episode became another data point supporting the view that scientists don't really know what they're talking about, that they scare us with wild claims only to walk them back later. This parallels the 3i Atlas situation in revealing ways. Both involve real science generating speculative scenarios that get amplified beyond their evidential basis. Both show how uncertainty, an essential feature of scientific inquiry, gets distorted in public discourse. Scientists say might or could or under certain assumptions. Media translates that into is or will, or scientists warn. The public receives catastrophic predictions presented with false certainty. When those predictions don't materialise, confidence in science suffers even though the science was tentative all along. The vacuum decay scare also highlights our appetite for existential threats. Why do these stories spread so virulently? Part of it is genuine fear. Vacuum decay represents ultimate helplessness. You can't prepare, can't escape, can't even know if it's happening until you cease to exist. That terror is primal. But there's also a strange allure. Imagining the end of everything is almost transcendent. It strips away petty concerns. If the universe might end tomorrow, your mortgage and job stress and relationship troubles suddenly seem trivial. There's liberation in that perspective, dark as it is. Apocalypse narratives provide psychological relief from mundane anxieties by replacing them with cosmic ones. The media's role can't be ignored. Sensational stories drive traffic. Fear sells. Outlets compete for attention in an oversaturated information environment. Publishing a measured, nuanced article about preliminary findings that might or might not indicate something interesting won't attract readers. Publishing universe could end tomorrow. Scientists terrified will. The incentive structure rewards exaggeration. Individual journalists might strive for accuracy, but institutional pressures push towards sensationalism. This dynamic guarantees that ambiguous scientific results get distorted in transmission from lab to public. Social media amplifies the problem. Algorithms prioritize engagement, which means content that provokes strong emotions spreads fastest. Fear, outrage, and shock perform well. Calm, rational analysis doesn't. A tweet saying new data suggests vacuum might be metastable requires further study gets ignored. A tweet saying the universe is ending right now gets thousands of shares. The platform mechanics select for misinformation, not through malice, but through structural incentives that reward virality over accuracy. The vacuum decay correction also struggled to spread because corrections are inherently less interesting than original claims. Saying we were wrong, everything is fine, doesn't carry the emotional weight of the initial scare. People who saw the first headlines might never see the retraction. Their belief that vacuum decay is imminent persists, shaping their worldview even though it's based on outdated information. This creates a cognitive landscape littered with zombie ideas, claims that have been debunked but refuse to die, because corrections don't propagate as effectively as errors. What can be done? Scientists need better communication training, learning to anticipate how their words might be misinterpreted, and crafting messages that resist sensationalization. Media outlets need stronger editorial standards, prioritizing accuracy over speed and clicks. Platforms need to redesign algorithms to promote reliable information over engaging misinformation. None of this is easy. The incentives are deeply entrenched. But the alternative is a world where every scientific uncertainty spawns a panic, where trust erodes irreparably, and where legitimate warnings get ignored because people have been burned too many times by false alarms. The vacuum decay scare connects to 3i Atlas because both demonstrate how frontier science becomes twisted into apocalyptic narrative. The comet is just a comet, but speculation about its mass and effects spirals into orbital chaos scenarios and ejection timelines. The vacuum is just the vacuum, but a detector glitch becomes evidence of imminent universal annihilation. In both cases, the distance between what science actually says and what the public hears is vast. Bridging that gap requires effort from all sides. Scientists must communicate clearly, media must report responsibly, the public must cultivate skepticism and numeracy. Until that happens, every cosmic mystery will be potential. Doomsday fuel. Part 15. The Year. Humanity realised the universe is not a calm place. 2025 will be remembered for many things, but perhaps its most significant legacy is a shift in perspective. For most of modern history, we've treated the solar system as a stable, predictable place. The planets orbit like clockwork. The sun shines steadily. Asteroids and comets follow known paths. This predictability bred complacency. We focused on earthly concerns, climate change, geopolitics, economics, assuming the cosmic environment would remain benign. Then came 3I Atlas, the third interstellar visitor detected in under a decade. That single object, regardless of whether it posed any actual danger, shattered the illusion of cosmic calm. We're not living in a quiet corner of the galaxy. We're living in a shooting gallery. The discoveries of 2025 extend beyond 3I Atlas itself. Spectroscopic analysis revealed unusual chemistry, carbon dioxide dominance, metal content, organic compounds processed by billions of years of cosmic radiation. These findings expanded our understanding of what interstellar objects can be. They're not just icy debris. They're messengers carrying information about distant stellar systems, about planetary formation under different conditions, about the chemical diversity of the galaxy. Every interstellar visitor is a free sample from another star, delivered to our doorstep for study. We should be celebrating that opportunity even as we assess potential risks. Advances in observational technology accelerated in 2025. The James Webb Space Telescope and other infrared instruments provided unprecedented views of 3I Atlas's coma and composition. Ground-based telescopes coordinated observations, tracking the object as it moved through the sky. Space weather monitoring networks expanded, watching the sun more continuously and with greater sensitivity. New gravitational wave detectors came online, probing space-time for ripples from cosmic collisions. Quantum gravimeters mapped Earth's gravity field with extraordinary precision. Each instrument added to our awareness, filling gaps in our knowledge, revealing phenomena previously hidden. The human response to these discoveries reveals something important about our psychology. We're drawn to dramatic narratives. A comet passing harmlessly becomes a gravitational wrecking ball in speculative scenarios. Solar flares become evidence of cosmic destabilization. Detector glitches become signs of universal doom. This tendency isn't pathological. It's adaptive in some contexts. Our ancestors survived by being alert to threats, by imagining worst cases and preparing for them. But in the modern information environment, that same tendency generates runaway fear and misinformation. We need to evolve new cognitive strategies, ways of thinking that balance healthy caution with rational assessment of evidence. 2025 also demonstrated the power of artificial intelligence in scientific prediction. Machine learning systems successfully forecasted solar flares with useful lead times. Similar approaches are being developed for seismic activity, atmospheric phenomena, and asteroid risk assessment. These tools promise to make the cosmos more manageable, less unpredictable, but they also create new vulnerabilities. Over-reliance on AI predictions could blind us to truly novel events outside the training data. 3I Atlas itself is a reminder that the universe contains surprises no historical dataset can prepare you for. We must use these tools wisely, recognizing their strengths and limitations. The vacuum decay scare, though brief, highlighted the fragility of public trust in science. Sensational headlines erode confidence when they're not followed by catastrophe. The boy who cried wolf dynamic makes it harder for scientists to communicate genuine risks. When legitimate warnings come, will anyone listen? The challenge is to communicate uncertainty honestly, while still conveying the importance of preparation. That's a difficult needle to thread. It requires nuance, patience, and a public willing to engage with complexity. We're not there yet, but perhaps awareness of the problem is the first step towards solving it. Looking forward, several futures seem possible. In the optimistic scenario, humanity rises to the challenge. We expand observational networks to detect interstellar visitors earlier. We develop rapid response capabilities to study them, or, if necessary, deflect dangerous objects. We invest in off-world infrastructure not as panic bunkers, but as genuine expansion of civilization. We use AI prediction tools responsibly, maintaining human oversight and judgment. We improve science communication, bridging the gap between researchers and public. In this future, 3i Atlas is remembered as a catalyst, the event that woke us up to cosmic reality and motivated productive action. In the pessimistic scenario, we squander the opportunity. Detection systems remain underfunded. Interstellar visitors continue arriving with little warning. Misinformation dominates discourse, making it impossible to coordinate responses to real threats. Governments classify predictions, hoarding information for strategic advantage. Public trust in institutions collapses entirely. When a genuinely dangerous object appears, we're paralysed by confusion and mistrust, unable to act collectively. 3i Atlas becomes a missed warning, the sign we ignored before disaster struck. The most likely future is somewhere between these extremes. Progress will be uneven. Some countries invest heavily in planetary defence while others lag. Some threats will be managed well, others mishandled. Misinformation and good science will coexist, competing for attention. Humanity will muddle through as we always have, learning slowly, making mistakes, occasionally rising to the occasion. 3i Atlas will fade from headlines but remain in scientific literature, a case study in how we react to cosmic anomalies, a test run for future encounters. What we know for certain is that the universe is not the calm, predictable place we once imagined. The galaxy teems with wandering debris, stars explode, black holes collide, interstellar objects pass through regularly. Our solar system sits exposed to all of it. We can't retreat to ignorance. We can't pretend the cosmos doesn't matter. We must engage with it, understand it, prepare for it. That's the legacy of 2025. Not panic, not doom, but awareness. We've been reminded that we live in a dynamic, sometimes dangerous universe. The question now is what we do with that knowledge. Do we succumb to fear and conspiracy? Or do we rise to meet the challenge, building systems and institutions capable of navigating cosmic uncertainty? The clock isn't ticking toward inevitable catastrophe. It's ticking toward a choice. Every moment we delay, we make that choice by default. 3i Atlas has passed, the next visitor will come, and when it does, we'll discover whether 2025 taught us anything, or whether we remain as vulnerable and unprepared as ever, staring at the sky and wondering what comes next.